Perfect. Well, since it is 11 o'clock, I think we'll get going here. So thank you everyone for attending. Really appreciate it. This is actually our second time hosting our TigerStream webinar series. As you all know, this is kind of a newer thing that we're doing. So the TigerStream series is an opportunity for us to share research that we are actively doing, things that's done in the past, and just a variety of different erosion sediment control practices that are out there to help spread the news and share the knowledge in a more accessible way that's not isolated to just conferences, so that you guys can learn about things whenever you want. So the fun thing about these webinars is we do record them, and once we are done with it, we will end up putting that recording on our YouTube page. So if you aren't able to attend our webinar, or if you want to rewatch it or share it with anyone, that you are able to access that on our YouTube page. And that does get sent out within a couple days after having this meeting. So again, thank you everyone for joining today or this month's speaker. We have Megan Armstrong. I have worked with her for the last 3 years, and she's been a great colleague and have completed our master's together. And now we're both doing our PhD, and she's going to be presenting on what she finished up with her master's on. So Megan, I'll let you go ahead and take the stage, but just as a reminder really quick, if you guys do have questions, you do not have the option to speak, to unmute yourselves and speak, but just go ahead and you can put in your messages in the Q&A button, and we'll address those at the end of the presentation. And otherwise, Megan, it's all you.
Awesome. Thank you, Janelle. And thank you everyone for being here on our second month of doing TigerStream. I'm really excited to be able to speak to you guys today about my master's project, something that I worked really hard on, and I feel like we got a lot of good data, good information out of it. So I'm really excited to be able to share this with you guys today. So my project was entitled Optimization of Sediment Basin Configurations using intermediate scale testing. So we use different basin geometries, volumetric and geometric, and different treatment methods to look at how these parameters affected sediment capture within the basin. So before we kind of get into my project and, stormwater in general, I wanted to give a little background about myself. So I went to Mississippi State University and got my bachelor's degree in biological engineering with an environmental emphasis. I recently, in the past year, finished up my master's degree here at Auburn in civil engineering, doing this project in the construction stormwater management group. And I also now with my PhD project, I work as an engineering intern for Fagan Consulting and sort of a liaison for Auburn University to Fagan. So to get into the project itself, this is a little overview about what I'll be going over today. We'll talk about the problem statement, overall research objectives, some literature review to give you guys some background. I'll discuss the methodology of the project. We'll go into all three different basin configurations, those intermediate scale basin configurations that we constructed and evaluated, results, and future testing. So obviously we have a problem. So over half of our rivers and streams and almost 3/4 of our lakes, ponds, and reservoirs in the US are impaired. So you might be thinking, well, what's impairing these waterways or waters of the US? And the EPA actually identifies sediment as one of the most widespread pollutants affecting our water bodies, along with nutrients and heavy metals, which it also can act as a transporter for. So in the construction realm of things, when you're starting construction projects, you're removing that topsoil and you are preparing to grade your land. And during that time, you might not have as much cover on the land as you would like. So this can cause higher erosion rates versus sites like agricultural or forested sites due to those construction activities. I mean, this can lead to 1,000 to 2,000 times higher than natural areas and 10 to 20 times more than your agricultural areas. So this soil erosion, this rainfall induced erosion can have significant downstream impacts, and it can create a lot of sediment loss on site. These are actually some pictures that I took through one of Dr. Perez's courses. We were able to go out on a site and evaluate it to see how these practices were implemented and how they were working. So we got to firsthand see the sediment loss due to this rainfall induced erosion. So also the downstream impacts, they can have, detrimental physical and environmental impacts. So increase of turbidity, which is harmful to aquatic life, the nutrient transport, which I kind of discussed a minute ago, loss of water storage, which can, subsequently lead to a higher risk of flooding. So there's a lot of negative downstream impacts that we're looking to avoid by using some of these practices that we've been using for years now. So my project specifically focused on sediment basins. So the purpose of these sediment basins are to capture and passively treat stormwater runoff by providing extended detention and promoting that gravitational settling within the basin. For that to happen, they need to have an inflow channel, a primary discharge outlet, and then some treatment methods in the basin, typically in the form of coir baffles. So why are these being used? And this kind of goes back to the EPA and their goals. They wanted to have restored water bodies and streams years ago, and that still is not completed to this day. So we're still working towards making some impact on cleaning our water bodies and making them be able to be used for their designed use. So the EPA actually enforces the Clean Water Act. So what this does is it established the NPDES program to regulate these discharges into the U.S. waters. And so for construction projects, compliance with these NPDES is achieved through the construction general permit. To have a construction general permit, you must lay out your erosion and sediment control practices in a stormwater pollution prevention plan. And so the construction general permit requirements, they want you to submit a notice of intent on sites that are greater than 1 acre of disturbance. And this requires, like I mentioned earlier, the SWIP for all the construction activities. So you're talking design, installation, and maintenance of these controls. Inspections to verify the compliance, and then also compliance with state, travel, and territory specific requirements. In Alabama, we have the Alabama Blue Book, which is a comprehensive guide. It's used in Alabama for planning, designing, and implementing these erosion and sediment control practices. It gives different layouts and descriptions, say in this case of a sediment basin, what are the components that are used, how are they installed, and what do they do to help prevent downstream sedimentation or to reduce erosion. So the construction general permit in Alabama, it states that you must have installed and stabilized the area prior to any other construction activities. You need to locate the basin outside of any waters of the state. So this means it shouldn't be in a channel or something of that nature. Provide enough storage for 3,600 cubic foot per acre of the contributory drainage area. Use outlet structures that draw water from the basin surface, such as a floating surface skimmer. And then to remove the accumulated sediment to provide maintenance when it's needed. So a lot of research has been done in the past decade, and there are some research gaps that we're trying to help fill and work alongside others to help make these practices really backed with the engineering design guidance. Because what these gaps can do. I mean, it can lead to, improper installation and guidance and improper maintenance, and downstream or down the road, you can look back and say, we put all these practices in, we spent all this money on it, but they're not working effectively. So we really want to maximize the efficiency of these practices for the amount of costs that operators are putting into their sites. So basin sizing guidelines, basin sizing itself, the size and shape does influence how much sediment is actually retained in the basin, and thus will help allow less sediment to be discharged through the spillway. So for volume design, you actually have two options. You can do the volume sizing factor, which I mentioned earlier, that 3,600 cubic foot per acre, or you can go with the hydraulic design, so the 2-year 24-hour event, and using that rainfall depth to size your basin. And in some cases, like in our area, in central Alabama, you would see basins that are designed with the hydraulic design. They could be up to 3 times larger than those for the volume sizing factor, due to our area and how much rainfall we get here. So the Alabama, the dimension requirements for those, for the basin itself, a length to width of at least 2 to 1. So you're allowing a longer period of time from inflow to outlet. A side slopes of greater than 2 to 1, horizontal to vertical, a depth of 2 to 5 feet, and then a max drainage area of 10 acres. To get into some of the components of the sediment basin and what an AU.ie sediment basin looks like, you would have some sort of channel or forebay. This directs the water into the sediment basin. If you don't have anything directing the water into the basin, you could get erosion, like I showed in those first few pictures of that site, where there wasn't exactly, a defined channel, so it can erode the sides of the basin. So to have that introduction channel in place is very important. As you can see here, this looks to be a 2 to 1 length to width ratio or greater. There's 3 coir baffles, so that's coconut coir baffles, a primary spillway, which consists of a floating surface skimmer, and a stabilized auxiliary spillway for any emergency flow. So what these baffles are able to do for our sediment basin is they not only reduce the amount of runoff energy that's entering the channel, slow that runoff down to create closer to laminar flows or slower velocity flows, it also distributes it across the width of the basin itself. So allowing sediment to be spread over the width of the basin and not concentrate towards the primary outlet, which is, in our case, the floating surface skimmer. And as you can see in this photo, this is a experiment we ran for one of our field days that we have at Auburn University, to show the importance of baffles and how they work. So this shows, if you have a concentrated flow coming in like that blue dye, without baffles, you're not spreading that concentrated flow throughout the width of your basin. It's really concentrated towards that primary surface outlet. So to get into a little bit of literature review, this is a modeling study that was performed in '99. This just kind of shows different basin geometries and how it's influenced by inflow to outflow point. And what we got out of this was that spreading the flow across the inflow of the basin could really increase sediment capture. So that E configuration there, that would be more like a level spreader, something spreading the flow coming into the basin itself. And we also saw the G and J, those configurations look like they worked pretty well. And really what both of those are doing is they're just they're increasing the time that the inflow has to go from the introduction channel to the actual basin outlet. So for For G, that would be using some sort of solid berms to actually lengthen the flow path. And in J, actually just lengthening the basin itself. Say if you were to use it in a roadside channel, a basin in a roadside channel, you would have more area to do a longer basin. And from this model study, it showed improvement with sediment capture. Another study by McLaughlin in 2005, this has to do with the energy dissipation methods. So what this was showing us was that sediment capture does depend on baffles and how many baffles are in. They use 3 different baffle materials, so a silt-fence material, a tree protection fence, and a jute coir. So this study showed that the coir baffles were most effective. So that's about that medium POA, percent open area size, in terms of if you're looking at the larger tree protection fence or the smaller silt fence material. And so this showed not only that the coir baffles were most effective, but that the first baffle was most efficient in reducing velocity and capturing sediment. So to get into the research objectives and the actual meat of this study that we did here, what we really, our goal was to see, can the standard sediment basin design approach be reconfigured to basically increase performance and reduce the overall costs of the project itself? So first goal is, develop small scale testing method or intermediate scale testing method and evaluate the sediment basin performance of each. So first we started off by evaluating those various geometric and volumetric basin configurations. Then we went into evaluating the performance of the treatments that were actually within the basin. And then we wanted to determine what was our overall most feasible and effective installation. And really the benefits for this intermediate scale testing that we did in the lab, it gave us the ability to confirm those proof of concepts before testing large scale. So this was a highly controlled environment. It was ease of basin manipulation. We were able to configure 3 different basin configurations in 2 years and run all these experiments on 18 different configurations as far as geometric, volumetric, and treatment method capabilities, to where, in the field, it would be much more challenging to do that, a lot more work and time, money, and resources, pretty much. So the overall testing regime that we followed here, we had phase 1 of our testing, which was done on our standard basin configuration. And when I say standard basin configuration, I mean this is our 2-to-1 length to width ratio basin that mimicked our scaled version of the 3,600 cubic foot basin. So we started out doing no energy dissipation, 3 coir baffles, lengthened flow path, single coir baffles. We introduced a level spreader and a baffle, and then we tested with no skimmer and flocculants. And I'll explain some more about those when we get to the actual methodology. So after that, we were able to determine the most feasible and effective installation, identify which one from phase 1 was our most effective. And then we went into phase 2 of testing, which included the in-channel and undersized basin, where we used some of those configurations that worked really well in the standard basin and mimic those in the in-channel. So that's our 10-to-1 length to width ratio basin, which had approximately similar volumes to the standard basin installation. So mimicked a scaled 36 cubic foot in-channel basin, 10-to-1 length to width, and then an undersized basin, which we used to kind of model more of a 1,800 cubic foot, or the previous design standard volume basin. And this was our overall, and then after that, we identified the overall most feasible and effective installation. So as far as basin designs go, We had a lot of different parameters on these basins. The main ones to look at here are the volume capacity. So our standard and in-channel basins had a volume of 114 and 100 gallons respectively. They all had the same depth, so that's a 9-inch depth, and side slopes of 2 to 1. So those parameters stayed consistent throughout the project. And then our undersized basin mimicked about half the volume of those first two basins. So that was about 52 gallons. And then for the use of flocculant, we did use flocculant in all three basin designs after we had performed evaluations on the other treatment methods. The flocculant we used was H30 by Carolina Hydraulic. We prepared this emulsion. We put 0.1 ounces of flocculant to 2.5 gallons of water. We agitated it and we let it rest. And then we pumped it into the basin at a controlled rate, depending on our storm volume size. And then as far as basin scaling, we wanted to really mimic real world conditions and what this could look like if we took it to a field scale test. So we wanted to make sure we accounted for everything that would be included in this testing. So we needed to make sure that the basin was scaled properly. And so for this standard basin, our volume scale was about 6.2 to 1. And then for the in-channel basin, it was also about 6.25 to 1. So they were very similar there. And then we used the same amount of storm volume for the undersized basin. So we did not need a scale for the storm event. So we started identifying what flow rate we were going to use by estimating a 60-minute peak runoff for just an arbitrary 1-acre drainage area in Alabama. And I say that to say that we wanted to use the rainfall depth and the curve number for this region specifically. So the rainfall depth we used was 4.5. Alabama's curve number we used for this location was about 88. And then we were able to use data from this hydraulic analysis from the Southeast states. And this was an analysis conducted by Run One in 2015. So he provided this data for us: rainfall, depth, and curve number, and then this equation to find the peak runoff 60-minute volume for this basin. So that ended up being 684 gallons per minute. Obviously, that's not going to work for our basin, so we use that scale that I previously talked about to now scale the flow rate back and to use something that would replicate a scaled version of a real case scenario. So our storm volume ended up being 7.2 gallons per minute. And again, this was tested in the in-channel, standard, and undersized basins. For our flow introduction system, we used split tubing to come up with 2 elbows in that top 8-inch PVC cylinder there. What that did was create more of a swirling effect to really combine the sediment and flow before entering the basin itself. We used a pressure regulator to control the flow here. So the overall conveyance system, we had that sediment-laden water mixture come in, and this is how it left the sites or left the basin itself. So through the spillway, we had a PVC pipe there that we cut and channeled it into these troughs. I'll talk to you about that later, but that was for our overall mass balance of the system to be able to know where the sediment was captured in each location. So the sediment introduction rate, we also wanted to mimic those real world conditions. To do that, we needed to know what was our overall inflow turbidity, how much turbidity did we need to kind of replicate that. And we used the Franklin study here to get an average inflow total solids of 3,268 milligrams per liter. And this ended up being about 6 pounds per each 30-minute test duration. And so for the soil classification, this was previously done. We found that we had 34% clay, 5% silt, and 61% sand, which gave us a sandy clay loam, and this was soil used from our research facility. So we wanted to scale the sediment, like I said, to replicate those real world scenarios. So we knew we had a sandy clay loam. We found the soil density, fluid density of water, and then we used average particle size diameters for each one to scale those back. So here's our first soil gradation, the actual soil gradation that came from the AU-SURF facility. The percent mass, which was found during the original soil gradation, and then the scaled soil gradation, which was found using Solver and Inventor. So we wanted to find what was the time that it took, say, the number 4 sieve to settle in that 3.5 foot basin, so something that would replicate real world scenarios, to the 4-inch sieve, what would settle in our 9-inch basin. So after we scaled our sediment, we needed to get the total amount of sediment and how much did we need for each test. We have that target concentration there from that Franklin County study that was in Alabama, our target storm volume. So this is just our flow rate times our test duration, which was 30 minutes. And then the sediment gradation that we used for each test. And so we just multiplied how much weight we needed by the total, the percentages of each sieve size. And this was with our scaled sediment gradation. And like I hit on earlier, this is our overall introduction system. So this is how we introduce the sediment into the system itself. We had an auger that introduced the sediment into that PVC at a controlled rate. It mixed in that column that you see in the middle picture there, and then it subsequently discharged into our intermediate scale sediment basin. So this is a video to kind of show you how that worked with those 2 elbows in that first PVC pipe, the auger going at a constant rate, and then how it was subsequently entered into the basin. So an overall summary about our testing methodology and how we came up with that. Our testing duration was 30 minutes. We had a flow rate of 7.2 gallons per minute, a sediment introduction rate of 92 gallons per minute, grams per minute, excuse me, and that gave us about 6 pounds of sediment for each test. Once we did the scaled sediment gradation, we found that we had now a sandy clay instead of a sandy clay loam. So that's why that is scratched out there. So as far as sampling, we sampled 3 different locations in this basin, an inflow sample to see what our turbidity was and what our total solids were over the duration of the test. The surface skimmer, so the outlet of that surface skimmer, and then the spillway outflow. The spillway outflow was what we used to compare most of these tests. Every single test used a spillway outflow system. Not every test used a skimmer, and I'll get into that more as the presentation continues. For our sampling intervals, this is for the standard and in-channel basins. That's why it says the 114 to 100 gallons basins. We had inflow samples that started at the beginning of the test and ran until the flow ceased to be introduced, which was 30 minutes into the test. We had spillway samples that started as soon as the spillway started overflowing. That was about 15 minutes for both of these basins. And then for the skimmer, we began sampling when the skimmer started to discharge. That was about 3 minutes into the test, all the way until about 4.5 to 5 hours. The sampling intervals differ just slightly for the undersized basin. This was due to the limited amount of volume that we had, almost half the size of both of those basins. So our spillway overflow started a lot quicker. It started at 6 minutes, and we kept that until 39 minutes, which was the same time that we kept it for the standard and in-channel basins. For sample processing, we did turbidity measurements and total solid measurements. So this was to give us a correlation, a comparison of how the turbidity and total solids related during the duration of the test. And also for sample processing, we did a comprehensive mass balance analysis to track where all the sediment was introduced into the system and where it deposited in 6 different locations within the basin. So those locations were Bay 1, 2, 3, and 4, so all within the basin, the skimmer, and the auxiliary spillway. So this was settled for 24 hours. The next day we would come in and we would pump it out from the top. We would dry the basin using heat lamps and then split the basin into the 4 separate bays. As far as the sample processing for spillway and skimmer, these were deposited into large troughs. So what we had to do for these is we flocked them. We put the same flocculant in there that we used for our flocculant testing. And we let it settle for 24 hours before pumping it out. After that, we were able to get it into these metal containers, dry it, and then subsequently weigh it. So now to kind of get into the fun part, more of the results and what we found in the study. So I'll go through each different basin configuration that we did for standard, in channel, and undersize, and I'll talk to you about them all specifically. So to start off, we want to talk about no treatment. So this is our standard basin design with absolutely no treatments in it. So no energy dissipators and no skimmer. And the reason that we wanted to do, or the reason that we did the test without a skimmer, was due to the spatial constraints for the undersized basin. We could not fit our skimmer in there. So we wanted to make these comparisons directly to that undersized basin. So that's why we did these. In no way, shape, or form in this study or in this presentation am I trying to get that skimmers are a bad idea. Skimmers are a great idea. We believe that they work. Properly sized skimmers do work. I'm just wanting to lay that out there because there were some configurations that we did not use these floating surface skimmers. So to get started on this, we have no treatment methods. What this R means here is the amount of sediment actually retained within the basins. And that's looking at how much we actually put into the basin versus, how much was captured in these areas. So, and then we found that for the O here, that's our outflow, our spillway, we found that there were 16% of that sediment that was introduced left through the spillway. So now we have the sediment retained. We have a skimmer, that's that orange S there, and then the overflow or spillway, which would be that blue, or that green O. And so this is a picture, when I was a new grad student, I didn't realize how much photography we were gonna have to do. So, and some of these, or I think just for this one specifically, I just had an older picture, so that skimmer does not replicate the actual skimmer that was used in this basin. We did use the same skimmer throughout all of the configurations that used it. So in this basin, we had no energy dissipation, but we did have the floating surface skimmer. And we found 82% sediment was retained within the basin, 6% left through the skimmer, and 12% left through spillway overflow. So in comparison to our no treatment methods that I just mentioned, this is a 4% difference of spillway leaving through the overflow. And like I mentioned earlier, we really used the spillway overflow to compare all of these basins to see how much sediment we would possibly be discharging offsite. So then we wanted to look at pretty much our AU.ie standard per se. So this is our 3 coir baffles and our floating surface skimmer. And for this, we found 88% capture within the basin, 5% leaving through skimmer discharge, and 7% leaving through that spillway outflow. So this is a big increase from both of those, or at least from the previous design that I mentioned. So that was just a skimmer. Now we're talking about 3 coir baffles, and that helped increase by about 5% that discharge from the overflow. So talking about that study that I mentioned earlier from the literature review, it said that the first baffle really did a lot of work in reducing velocity and for sediment retention. So we wanted to look at what would a single coir baffle look like in our setup. So what we found here is that with the single coir baffle instead of 3 coir baffles, we were able to retain 86% of sediment. So that's just a 2% decrease, and just a 1% increase in that spillway overflow to make it 8%. So not too significant of a change here. We saw that, 3 baffles could be comparable to 1 baffle. And then talking about the modeling study that I mentioned in the literature review before that, we saw that increasing the flow path from inflow to outflow for the sediment particles could increase the amount of sediment we captured. So we wanted to do more of a serpentine or elaborate flow path. So as you can see in the little icon down there, the flow was supposed to go in between those serpentine baffles and create a longer flow path for it to have from inflow to outflow. And with this configuration, we were able to see 89% of sediment retained within the basin itself and 7% overflow. So no change from the first 3 coir baffles there as far as overflow spillway looks. And another study that we looked at in New Zealand, it showed the effects that a level spreader could have on sediment retention. And so we did want to try this configuration here. This level spreader is at 9 inches. So maybe in future studies we would do a level spreader with maybe different dimensions, because in this one we didn't see any significant results as far as sediment retention within the basin. It was a little bit less than our coir baffles, but like I said, if we did this in field scale, we would probably kind of change up the height of that level spreader that we put in. So we did want to see what a level spreader would look like with a single coir baffle. We thought maybe the level spreader was, since it was the same height as our spillway, maybe it was just discharging all of that incoming water straight out the spillway itself. We didn't really see a big increase here either, but like I said, when we do tests at the facility, if this becomes a large scale project, we would probably change the height of that level spreader to create some better impoundment. We also tried an impervious check dam. We actually got pretty good results from this. We only did, however, we only did 1 test for this configuration. It just didn't mimic field scale as much as we hoped it would, even though you can see that those larger sediment granules are captured upstream of that rock check dam. But we did see 88% sediment retention within the basin here, with 9% on the spillway overflow. So after we tried all of these, we really wanted to see what could we do as far as turbidity goes. We wanted to try flocculant and a single coir baffle. We know flocculant has helped immensely, chemical flocculants have helped immensely with turbidity reduction downstream after the spillway outflow. So what we did here is we had that flocculant emulsion that I mentioned earlier pumped in at a specific rate, and this was dependent on the amount of storm volume we had, and we got really good results for this configuration. We had 94% sediment retained within the basin itself and 3% sediment discharged throughout the spillway, which is unlike we had seen in any of the other configurations. So this gave us a lot of hope. We thought, if we replicate this in the in-channel and undersized basin, we should get really good results. So to move on to that in-channel basin, this would be, a basin found, say, in a roadway median and a roadway channel. How would this look? And so our goal was to increase the residence time, or the particle flow path length from inflow to outflow. Here we see that there's an 82% of sediment that was introduced into the basin was retained within the basin itself, and 18% discharged through the spillway. So this is a 2% increase in the sediment discharged to the spillway when we compare it to the first basin that I mentioned, the standard basin with no treatment methods. And we do believe this could be because of maybe an increased velocity within the basin itself due to its length to width ratio. But again, nothing too significant here as far as comparisons to that standard to in-channel basins. They did work similarly. So we wanted to try the single coir baffle like we did in the standard basin. This one was with no skimmer, again, to make those comparisons to the undersized basin themselves. So we found here that the amount of sediment retained within the basin was 88%, which is, and then, I'm sorry, 12% through the spillway outflow, and this is a 4% increase in sediment discharge through the spillway when compared to that single basin with that standard basin with a single baffle and a skimmer. So that one did have a skimmer with it, which is one reason why this overflow turbidity is increased, or amount of sediment is increased. Again, we wanted to try that AU.ie configuration, or the AU.ie standard with the 3 coir baffles in our in-channel basin itself. We had 86% retained within the basin, 5% leaving through the skimmer, and 9% discharged through the outflow. And again, this was a 2% increase compared to the 3 baffles and skimmer for the standard basin. We also did try a single coir baffle. This did include a skimmer. And what we found again was the same thing, 84% retained within the basin, 9% overflow through the spillway. And this here was a 2% increase compared to the standard basin with a single baffle and a skimmer. So we got pretty consistent results with these 2 basins and how they performed compared to each other. Again, we wanted to try that flocculant. We knew it worked really well in the standard basin, so we wanted to replicate it in our in-channel basin. We did a configuration with flocculant, a single coir baffle, and this one contained no skimmer. So you're looking at 95% retained within the basin, 5% through overflow. Again, we wanted to do this with including the skimmer to see what effects that would have on it. We saw 2% through the skimmer, 94% retained, and only 4% discharged through the spillway itself, which made it the most efficient in-channel basin configuration that we tested. So for the undersized basin, we were really excited to get to do to this part of it. We really wanted to see what were the comparisons between those larger volume basins and the smaller volume basin, and how would it look with no treatment methods. And we found with no treatment methods, we were retaining 64% of sediment. And 36% was leaving through the spillway overflow. So this is a 20% increase. I mean, this is a huge increase compared to the other 2 basins that perform pretty similarly. 20% increase discharged through the spillway when you compare it to that standard basin with no treatment configurations, and 18% increase when compared to the in-channel basin. So again, very drastic results here. We also wanted to try it with the single coir baffle. That seemed to work pretty well in our other 2 basin configurations, so we wanted to see how it could improve sediment capture within this basin. And we were able to see 73% retention within the basin, so an improvement from no treatment methods at all. And then 27% leaving that overflow spillway with the baffle. So a 19% increase when compared to that standard basin with a single baffle, and 15% increase when compared to the in-channel basin with a single baffle. So this was one of our favorite ones that we ran, I guess you could say. We were really excited to see what can flocculants do for an undersized basin with the single coir baffle. Are we gonna really reduce that turbidity downstream, or reduce the amount of sediment leaving the basin itself? And how big of a change would this be? So for flocculant configuration, we were able to get 91% of the sediment introduced retained in this basin. And again, this is the same storm volume that we introduced into the standard and in-channel basins. So the same amount of storm volume was sent through this basin, almost 6 pounds of sediment, just like the other configurations. So retaining 91% of that sediment was huge. We're almost working as effectively as the flocculant installations for the standard and in-channel basin. And this is actually an improved sediment retention value when compared to the aub.ie configuration, the 88% for those 3 coir baffles in the standard configuration. And then here we saw that there was 9% through spillway overflow. Like I said, we use this spillway overflow number to compare across all basins, since they didn't all contain those skimmers. So here's an overall efficiency summary for the 18 configurations that were tested. So in the yellow here, we have all the standard basin configurations. In the red or pink, we have the in-channel configurations. And in the blue, we have the undersized configurations. And you can see from these configurations, each of their outflow spillway percentages, so how much of that sediment that we introduced was discharged through the spillway. And we really wanted to highlight our flocculant, or chemical flocculant configurations here. So we have 3% leaving the spillway outflow for the standard basin. We have 4% for the in-channel basin, and 9%. So those numbers are a lot closer than we were when we were looking at the undersized basin with no chemical flocculants added. This graphic also shows the flocculant compared to no flocculant for the spillway turbidity reduction. So for the standard basin, we have 3% discharge to the spillway using flocculants, and then that's compared to 8% without any chemical flocculant treatment. In-channel basin, 4% using those chemical flocculants, 9% without the chemical flocculants. And then for the undersized basin, one of our more significant values that we got for this study, 9% through the spillway outflow, using half the volume basin, when compared to 27% without the chemical flocculant treatment. And that's for that. These are all without the flocculant treatment. Those are all with the single coir baffle, to make those comparisons there. And along with the amount of spillway, or the amount of sediment discharged through the spillway, we were able to see what are the installation costs of these. So we used a basin, assuming just a 1 acre contributory drainage area, and we assumed just a standard square footage around each of these basins to provide costs for land. And we did include the amount of the cost of chemical flocculants in each of the chemical flocculant configurations, as well as skimmers for each. So we took into account all of these, used aub.ie bid prices from past projects, and we were able to find that the standard basins can average around 23,000, in-channel basins around the same, but to use less land footprint for the undersized basin, we're talking about $17,000 per basin. This is a pretty big decrease, almost $6,000 here. And if you think about all the basins that are built in the state of Alabama or just in the US, that's a lot of money you could save on these projects. And here we wanted to do a direct comparison from our AU.ie standard to our undersized basin with chemical flocculants use. And again, there's, you know, a little over a $7,000 difference here from what we currently use to what, you know, would also work or could also work depending on how this experiment looked in the field. So to kind of get into the results and a breakdown, like I just said, we did that mass balance. We really wanted to see how much sediment was captured in each of those 6 locations in the basin. Your Bay 1, that's in blue here, your Bay 2 in red, Bay 3 in yellow, Bay 4 in green, your skimmer outflow in blue, and then your spillway that's in gray there. And what we found with this that I thought was pretty interesting, you can see the changes in Bay 1, and you can see the changes in the spillway outflow. But using those chemical flocculants, you're capturing, or with this study, we found that we could capture almost 70% of the sediment going into the basin just in that first bay, just in that first portion of the basin. So that's pretty significant to us. And then you can see on the side, I provided all the icons so you can kind of match it up to which configuration that we're discussing here. And again, for the in-channel basin, this was another thing that really stood out. You can see how providing those treatment methods, those energy dissipators in the form of coir baffles really helped increase the amount of sediment retained in Bay 1 and also decrease the amount of sediment leaving through your overflow spillway. But when you put the chemical flocculant in, again, the basin showed that they can retain almost 70% of the sediment within that first bay. Then to go to the undersized basin and where the sediment was retained, again, you can see the same pattern here. There's more sediment discharged through the spillway for those first couple configurations. That the first configuration without any, that's 37%, 27% for the configuration using the single coir baffle, so that 10% difference there just by using that baffle. And then over a 20% difference in what was retained in Bay 1. But then we look at the flocculant configuration, and you can see, again, almost 70% of the sediment introduced was retained within that first bay. So some conclusions about the project. We did see, the inclusion of coir baffles. It can enhance that sediment capture by up to 10%. We also saw that, reduced volume basins, along with these chemical flocculants, may provide equivalent, even or greater sediment capture to those typical larger basin designs. And again, this could, promote some cost savings. So for future research, what we want to pursue down the line would be those large-scale field-scale tests to replicate this study in the field to see, does it work as we think it would from our intermediate setup to a large-scale setup. Also, varying length to width ratios, including doing the 2-to-1 length to width on the top dimensions. And I apologize if I didn't mention this earlier. The 2-to-1 length to width was on the bottom of each of these dimensions. So evaluating some different ratios as such, and field monitoring basins to get more data to run these field scale tests. And that is all. That's all for my project. I really appreciated y'all's time today, taking the time out of your day to listen to me present to you what I did for my master's research. If you have any questions, I can't answer those now, but thank you all.
Thank you, Megan. That was a great job. So for questions, we have one starting off with Derek Hutton. He had asked, now that you have gone over other scenarios, can you explain the S8 no treatment slides a little bit more? He's wanting to know if 80% retained was a good value and why there was no spillway in that scenario.
Okay, and I'm sorry that I didn't provide that clarification. On S8, there was a spillway. There was not a skimmer included in that setup. There was an auxiliary spillway, so we did look at how much was leaving that auxiliary spillway. The reason that we didn't have any treatment methods, including the skimmer itself, is because when we did our undersized basin testing, we could not fit, due to spatial constraints, we could not fit the same skimmer that we used in those previous experiments, and we did not want to change the size of the skimmer. So that was just strictly to make those comparisons from the standard and in-channel basins to that undersized basin. I would say 80% could be an okay value, but I mean, you're in the field, we're talking about a lot more sediment than obviously 6 pounds. I mean, this is a lot of sediment, so you could be discharging, a lot of pounds of sediment downstream if even if you're only at 80% capture efficiency. So we really did want to look at different ways that we could increase that capture efficiency.
Our next question is, um, how often should you clean out the sediment in the retention basins without damaging their configurations, baffles, or the skimmer? And then if you do damage any of those, how often would you have to replace them?
I'm guessing this is in a more field scale setting that they're talking about. I believe it's once the basin is about half full of sediment, you're supposed to dredge that out and clean it in the field. And I would have to get back to you on the way that would affect the actual treatment methods within the basin themselves.
Currently, we don't have any other questions. If you do have questions, please feel free to hit that Q&A button at the bottom of your screen, and then we'll go ahead and get those answered. I know we have just a few more minutes left for this webinar, and I know a lot of you probably have somewhere else to be. But in the event that you do have a question that you don't have a time to throw in here, you can feel free to email us or shoot Megan an email directly, and we'll be happy to answer your questions. Additionally, if you do have to hop off before you can hear the answer to your question, if you do type it in there, then again, we do have these webinars recorded and we do put them on our website. And I'll go ahead and send that out in the group chat for everyone. But for your reference, our YouTube page, if you just go to YouTube and you search up AU Stormwater, we'll be right there, and we'll have these webinars posted on there. But in the meantime, thank you again, everyone, for joining. And once again, this is kind of a newer thing that we're doing. And so we are looking for volunteers if anyone is interested in sharing some of their knowledge or anything that they want to get out there and present for us, then shoot us an email. We'd love to hear. Or if you have any recommendations on who a good speaker would be, we would appreciate that as well. Additionally, if you have any suggestions of things, the topics that you want to hear about, if you know some of the research that we have done in the past and you want to hear us present about it, we'd be happy to dig that up, hunt down our past researchers if that's the case, and get them on here to present as well. So again, anything that you want to hear from us, please reach out to us and we'd be happy to share all of that with you. But otherwise, how do we get, the PDH hours. I don't know if Dr. Perez is able to answer that one for us.
Yes, so there's going to be an email that goes out in 2 days. It's an automated email, and it's going to have a link where you're going to click on it. It's going to take you to a Canvas page, and you just have to put in your information, and you'll be able to download your PDH certificate there immediately. And if you haven't gotten it for your July, it's the same process. It'll be the same link. That should work for both.
Perfect. Well, again, I think that wraps up our time today. Again, if you had a question that you weren't able to get answered, please reach out to us. Otherwise, thank you so much for attending. We really appreciate it. And thank you again, Megan, for presenting on your topic. We really enjoyed it. Thank you,
you,
everyone.
guys.